Good morning, everybody. Welcome to IB Buddy, Grade 9 Math, Unit 1, Number Sense, Topic 1, Number Sets. So let's get on to what is a set. A set is essentially a collection of objects or numbers where order does not matter. So if we think about it this way, if we have an apple, you can't have -1, -2, or -3 apples. That's just not possible. That's a set. Because that set says that we can only have greater or equal to 0 apples. So we could have 0, 1, 2, 3, and above. But we can't have less than 0. That's a set. We can also think of it as measurement. If we have measurement like this whiteboard is 1.5 meters, let's say. You can't have -1.5 meters. That's not possible again, because a set length or measurement is just continuous. So if you get a word problem on your math test and it tells you the measurement and you somehow get -5, your teacher's gonna be like, what are you saying? And then fail you. So we have some examples of sets. So it can be blue, green, red, yellow. That's a set. 3, 4, 5. That's also a set. And 5, 3, 4 as well as a set. But as you see here, you see that 3, 4, 5 is the same as 5, 3, 4. That's where order does not matter comes into play. Here, this is just a more ordered version of this. This is just like messy, unordered, disorganized. You see that numbers 5, 5, 4, 4, 3, 3. They all contain the same numbers in each set. It's just one is more ordered than the other. That's why sets are not lists. Lists are ordered, like number 1. Number 2, number 3. Sets can also be number 1, number 2, number 3. But it also can be number 3, number 1, number 2. It's more like this. So now that we know what a set is, let's get into what is a subset. So a subset contains only the elements that are already found in the parent set. We say parent set because this can also be classified as a parent set. This is either, you can say it's a set, but also a parent set. So if we see here, subset, the word subset, it has sub in it. Sub means like something, like a smaller version of the set. A smaller version of a set. That's a subset. So an example is we have the parent set, aka the set, 12, 2, 8, 6, 4. Again, it's not in order because sets don't care about order. So the subset could be 8, 4, 2 because it's a smaller version of the set and it has the same numbers that are already found in the parent set. 8, 8, 4, 4, 2, 2. 4. That can also be a subset. It's a smaller version of the set and already has 4 here. 4, 4. The subset can also be 2, 2, 4, 4, 6, 6, 8, 8, 12. But you realize that, wait a minute, this is just a more ordered version of the parent set. It has the same exact numbers, it's the same size of the parent set. And for that, you're right. The subset can also just be the set. You can have the same exact values of the parent set. That's also considered a subset. What a subset cannot be is 2, 4, 8, 10. Why? Because we see here 2, 2, yeah, that checks out. It's a smaller version of the set. And also, we have 2, yep, there's 2 here. 4, yep, we have 4 here. 8, yep, we have 8 here. But 10, we don't see anywhere in this set, in this parent set, a value of 10. And that means that this subset is invalid. That this cannot be a subset of this parent set. So to that we say, no, you're not a subset of this parent set. So again, if you haven't caught the hint, elements in the subset must contain the elements in the set or parent set. So now let's move on to set notation. For set notation, we're using curly brackets, which are these, commas, you already know, and ellipses, ... So we'll use these by doing practice examples. So we have write the set of integers from -3 to 4. So we first start off with curly brackets to build the set. So you just do a little curly bracket, that's a bad curly bracket, and then integers from -3 to 4. So let's just write -3, and then to separate your numbers, you don't write -3 and then -2, -1 like that. You need to separate these to make to let people know that this is like not like joined. It's not -3 minus 2. So you use a comma to separate these numbers. So -3, -2, -1, 0, 1, 2, and 3. And that's how you would write the set of integers from -3 all the way to 4. To 4, come on. Okay, wait. Messing up. -3 to 4. -3 all the way to 4. So now let me introduce another practice example which will help you understand what ellipses are. Alright, so now we have the other practice example, write all natural numbers less than 12. So now we know that, I'll get into this later, but natural numbers are essentially counting numbers that don't include 0. So use 1, 2, 3, 4, 5, etc. And there's no negative numbers. So you would write all natural numbers less than 12. It doesn't say less than or equal to 12. It just says less than 12, which means that 12 is not included in the set. So go from 11 down to 1, because 0 is not included in the set of natural numbers. I'll get into that later though. So let's just focus on the set less than 12. So of course, to build a set, we use the curly brackets. So we use this. Again, I don't have the best curly brackets. And then to separate numbers, we use commas. So all natural numbers less than 12, start with 1, comma, 2, 3. And then using ellipses to speed up time, you can just use ... and then 11. And then end it. So what this ellipse means, that it's 1, 2, 3, and it follows this pattern all the way to 11. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then 11. So sort of like on and on until this number. Now let's move on to another example. Alright, now for this practice problem, we have all multiples of 5 from 5 to 40. So what that means is from 5 to 40, we find all the multiples of the numbers that are multiples of 5. So of course, first to start the set, we use curly brackets. So let's just do that, curly brackets, and then 5 to 40. So 5 is a multiple of 5, so you write that. And it starts from 5. And then 10 is also a multiple of 5. 10, because if you do 5 times 2, that's 10. 15, 5 times 3, 20, 5 times 4, 25, 5 times 5, 30, 5 times 6, 35, 5 times 7, and 40, 5 times 8. Because it says from 5 to 40, so we stop at 40. And then end off our set. And this is also a set. And we write all multiples of 5 from 5 to 40 like this. 5 to 40. And these are all multiples of 5. Alright, moving on to empty sets. So empty sets are sets that contain no elements. So a further introduction to what elements are. So they're essentially the amount of objects in a set. So if we have this, we have 1, 2, 3 objects in this set. So that means there's 3 elements. Red. There's just one object, which is red. So how to check if it's an object is if it's separated by a comma. Every time it's separated by a comma, that single thing is one element. So you see 1, that's separated by a comma, so that's another new object. 2, that's separated by a comma, that's another new object. 3, there's 3. Here, it's not separated by a comma, so this is all just one object, so 1. And then here, there's 1, separated by a comma, 2, 3, 4. There's 4 elements. So now, if you get problems like the amount of, I know you can't see this really correctly, it says amount of presidents born in 3000. Right now, it's 2025. 3000 is in like around 1,000 years. We can't time travel to the future to see how many presidents are born in the year 3000. So with this word problem, we'll just write this. Not this, because this signifies that there is an object, because in this set, it signifies that there is one object, aka one element, so an answer. But there are no solutions to this answer, because you can't time travel to the future to find out how many presidents there are. So it would just be like this. No curly brackets, nothing. Just 0 with a cross. So then again, a set of even prime numbers greater than 2. There are no even prime numbers greater than 2. So again, you just do this, boom, and you're done. Alright, now we have symbols for number sets. So each of these symbols represent rules. So sets, so if we have like R, N, those represent rules. So first we have N. N means natural numbers. So natural numbers don't equal 0, are not negative numbers, and are not decimals. So it's like 1, 2, 3, 4, 5. They're counting numbers. Then we have whole numbers, which is expressed with W. W, like that. And they're just like natural numbers, but they equal 0. So it's 0, 1, 2, 3, 4, 5, and beyond. Then we have integers. Integers are just like whole numbers, but they also now include negative numbers. So -1, -2, -3, 0, 1, 2, 3, 4, 5, and beyond. But they don't contain decimals. Then we have rational numbers, which are just like integers, which they include 0, they have negative numbers, but this time it also includes decimals. But instead of saying that it includes decimals, we usually commonly say it can be expressed as a fraction. So 0.3 is essentially 1/3, you could say. So that is also a fraction. So irrational numbers are just numbers that can be expressed as a fraction. 4 can be expressed as a fraction. If you have, if you have 4 over here, 4, it can be expressed as a fraction. 4 is 4 over 1. That's expressed as a fraction. Because 4 divided by 1 is just 4. So this is expressed as a fraction as well. So essentially, if you want to keep it simple, all rational numbers are all numbers that can be represented as a fraction. Then we have irrational numbers, which are represented most commonly by p/q, but it can also just be p or q apostrophe or p/q, whichever. You have to ask your teacher what they prefer. So essentially, irrational numbers are numbers that cannot be expressed as a fraction. So pi cannot be expressed as a fraction. E cannot be expressed as a fraction. And square root of 2 or square root of 3 or square root of 5, stuff like that, you can't express as a fraction. And then we have real numbers, which are just like, look like this on like on a set. It says like find real numbers, stuff like that. Real numbers are essentially all numbers on a number line. A number line is all numbers from 0 to infinity and 0 to negative infinity. So it encompasses all these rules. So it can include natural numbers, so like 1, 2, 3. It can include whole numbers like 0. It can hold integers like -1, -2, -3. It can hold rational numbers like 1 over 3, 2 over 3, 3 over 1, stuff like that. It can also contain irrational numbers, so like pi. Pi is like 3.141592653, etc. 3.14159, that's still a real number. It can still be represented on a number line. Euler's number is like, I think like 2 point something something something. It can still be represented on a number line. Square root of 2 is like 1 point or something like that. That still can be represented on a number line, because those are like technically all decimals, but like never ending. So real numbers are essentially just encompassing all these rules. It can be all these. So it's sort of represented by this simple chart. So n, natural numbers, is the first thing. And then whole numbers. Whole numbers can also be natural numbers. And then higher up on the list are integers. Integers can be whole numbers and natural numbers. And then we have rational numbers, which can be integers, whole numbers, and natural numbers. And then we have real numbers, which can be rational numbers, integers, whole numbers, natural numbers, and also I forgot to write irrational numbers. So p/q, it also can represent that. But the reason I didn't write p/q, like p/q can be rational, integers, this stuff, because those are sort of never ending. It's like 3.14159, that can't be expressed as a fraction. So q, it sort of contradicts q. So p/q cannot be q, z, w, n, especially q, because those numbers can't be a fraction. So that is its own separate category, but real numbers are also irrational numbers. That's essentially like the hierarchy. So we can show you, so natural numbers are like 1, 2, stuff like that. Whole numbers can be 0, 1, 2. And then integers can be -2, -1, 0, 1, 2. Yeah, 2. And then here, rational numbers, they can be -1 over 3, 3 over 1, stuff like that. Decimals, yeah, like 0.33, stuff like that. And then we have irrational numbers, which like pi, Euler's number, square root of 2, and then real numbers, which are all of these. So it can be decimals, expressed as fractions, negative fractions, like every single number, 1.2, 2, 1, 0, everything. Pi, Euler's number, stuff like that. All of these. So that's all like the rankings. Like, as you can see, every time you move up and up, you unlock new, you could say, abilities, new powers. Like here, it didn't have 0, then it had 0, then it unlocked negative numbers, then it unlocked decimals, aka expressed as fractions. This one is sort of an exception, that's why I put it here. And then real numbers unlocks all these rules. So these are essentially what these symbols and number sets mean. So if you get like a question like find all whole numbers that start from 0 to 5, you'll know it's just 1, 2, 3, 4, 5. But if it says find all integers or find all rational numbers from 0 to 5, it would be like 0.1, 0.2, 0.3, and then it's like infinite, because you can make decimals infinitely long, like 0.333, 0.33331, like that. So that's essentially what these number symbols are, number set symbols. Alright, now we go into application of number set symbols. So if we get a question, all whole numbers are natural numbers. So this, we would say, is false. Why is it false? Because whole numbers contain 0. Natural numbers, if you remember, don't contain 0. They're 1, 2, 3, 4, 5. Well, whole numbers is 0, 1, 2, 3, 4, 5. We have, now, every prime number is a rational number. That would be true. True. Now, why is that true? Because rational numbers, let's write rational numbers. Alright, rational numbers first can be expressed as a fraction. So every prime number can be expressed as a fraction. 5, like 7, these, or like 11, stuff like that. These are prime numbers, but they can be represented as a fraction. If you just do this over 1, 7 over 1, 11 over 1. These are all represented as, or expressed as fractions. So this is true, that every prime number is a rational number, because every prime number can be represented as a fraction. And then we have the set of integers is a subset of the real numbers. So we're saying that the set integers, so we write here integers, set integers is a subset of real numbers. So subset is a smaller version of a set. So you're saying that Z is sort of like a smaller version of the set of real numbers. And that would be true, because if you remember, real numbers are encompassing every single number symbol, number set symbol. So yes, this is true that Z is a smaller version of real numbers, since real numbers do contain negative numbers and include 0 and include decimals and all that stuff. But here it's saying that integers are 0 and negative numbers and positive numbers, and real numbers, they also do have negative numbers and 0 and positive numbers. But they also have decimals. But you're saying that integers is the subset of a smaller version, so you don't include the decimals. So this is true. Alright, so now we have counting the amount of subsets. So if you have a set and you want to know the possible amount of subsets you can create with that set, this is the formula. So it's 2 to the exponent n. So n means the amount of elements in that subset. So in this set, there are 1, 2, 3 elements in this particular set. So then you plug in 3 with n, so there would be 2 to the exponent 3, which is 8. So there's 8 possible subscripts you can create with this set. And you have to make sure that this formula includes having 0, like nothing. Because if you know, a subset of ABC can also be nothing. A subset of like any set has nothing, because like any set, like here, a smaller version of it can also be nothing. So that's why when we have list them, nothing, and of course we don't put the curly brackets, never put the curly brackets, because if you put curly brackets here, remember that signifies that there's one element, but we want to signify no elements, so we remove the curly brackets, so it just becomes this, symbolizing nothing. And then we have A, B, C, AB, AC, BC, and ABC. If you were wondering why there's no BA and BC and CA and CB, it's because if you remember, sets don't care about order. So AB is the same as BA. Oh, that's a wrong thing. Wait. BA. Okay. So AB is the same thing as BA. So that's why AC and CA, we just set it as AC. Just one singular set. We don't have to point out another set, AC and ACA. We just do AC. And then we have the word problem. A teacher gives you 4 project options. How many possible project options can you choose, including choosing none? So you plug in 4 and you get 16 possible options. But if the word problem asks you how many possible options can you pick without choosing none, then you subtract this by 1, because this counts as one of the available options. So you just subtract by 1 to get rid of this one. So that would be 15, actually. So that is it for counting the amount of subscripts. So thank you everybody for watching this video. This video is quite long because it's talking about the basics and fundamentals of math here. Not the absolute basics, but what you need to know in grade 9. So these videos are going to be quite long because it has a lot of information, and if you don't understand in depth, you're going to have a lot of trouble. So if you have any questions, leave them in the comments down below, or join our Discord server and ask questions there. Sometimes we'll be in voice chat or voice call, whatever you call it, and we'll be there helping you out, tutoring you guys. If you need to reach out to us, you can email us. Of course, subscribe to us, follow our other social medias, Discord, TikTok, Instagram, and I think I'll see you guys later. Peace!